Next, NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again after months of spouting gibberish. The spaceship left the solar system in 2012.
NASA says its Voyager 1 probe, the most distant human-made object in the universe, is once again sending usable information to Earth after months of transmitting gibberish. The spaceship, which left the solar system in 2012, marks a historic milestone as one of only 2 man-made objects to venture beyond our solar system. Voyager 2, NASA confirms, is now in the space between stars, having exited the Sun's protective bubble known as the Heliosphere. After an incredible 45-year journey through uncharted reaches of space, Voyager 1 has gone beyond the boundaries of our solar system. What it has discovered is mysterious and shocking, revealing strange signals and phenomena at the edge of interstellar space. These groundbreaking findings challenge long-held scientific beliefs and may hold the key to unraveling cosmic mysteries that have puzzled humanity for centuries. The Voyager program, launched by NASA in 1977, stands as one of the most successful and enduring achievements in space exploration history. Originally designed to take advantage of a rare planetary alignment, the twin spacecraft, Voyager 1 and Voyager 2, began as a short-term mission to explore the outer planets. However, this mission evolved into an epic multi-decade journey, carrying the spacecraft to the very edge of our solar system and beyond. The idea for the Voyager missions emerged in the early 1970s when NASA scientists recognized that a rare alignment of the outer planets, occurring only once every 176 years, would allow a spacecraft to utilize gravitational assists. This method would slingshot the spacecraft from one planet to the next, significantly reducing the time and fuel required for exploration. NASA seized the opportunity by designing 2 spacecraft capable of conducting a grand tour of the outer planets. The primary objectives of the Voyager missions included studying Jupiter and Saturn, investigating their atmospheres, moons, and rings, and exploring their magnetic fields and radiation environments. Additionally, the mission aimed to extend exploration to Uranus and Neptune, specifically with Voyager 2. Both spacecraft were equipped with 11 scientific instruments to study magnetic fields, cosmic rays, plasma waves, and planetary atmospheres, among other phenomena. Cameras and imaging systems allowed the Voyagers to capture unprecedented close-up photos of the outer planets and their moons. Voyager 2, launched first despite being designated as 2, followed a slower trajectory that enabled it to visit all 4 outer planets, Jupiter, Saturn, Uranus, and Neptune. This extended journey was made possible by using gravity assists to boost its speed without additional fuel. Voyager 1, on the other hand, took a faster trajectory to reach Jupiter and Saturn more quickly, ultimately exiting the solar system after its encounter with Saturn. Before the Voyager missions, knowledge of Jupiter and its moons was limited to ground-based observations and earlier flybys by Pioneer 10 and 11 in the 1970s. While these missions provided valuable insights, they only hinted at the Jovian system's complexity. The twin Voyager missions aimed to build on these findings, capturing detailed images and conducting closer examinations of Jupiter's atmosphere, moons, and magnetic field. The discoveries made during their 1979 encounters with Jupiter far exceeded expectations and transformed scientists' understanding of the planet. For example, the Great Red Spot, a massive storm large enough to engulf 3 Earths, had been observed for over 300 years. It was previously thought to be a relatively stable atmospheric feature, similar to a high-pressure system on Earth. However, Voyager's high-resolution images and data revealed the storm's dynamic nature, with swirling clouds and turbulent eddies indicating powerful atmospheric forces at play. The winds within Jupiter's Great Red Spot reached speeds of up to 400 miles per hour, 644 kilometers per hour, making it one of the most intense atmospheric phenomena in our solar system. Instead of being a stable, unchanging structure, the Great Red Spot has been observed to constantly shift its shape, suggesting it is highly dynamic and possibly evolving over time. This newfound understanding of the Great Red Spot's complexity challenged prior assumptions and led to new theories about Jupiter's atmospheric dynamics and the longevity of large-scale storms. Before the Voyager missions, Io, one of Jupiter's 4 largest moons, the Galilean moons, was believed to be a cold, cratered, and geologically dead world, much like Earth's moon. Scientists expected its surface to be heavily cratered and unchanged for billions of years. However, Voyager's close-up images of Io revealed a revolutionary discovery. The moon was geologically active, with active volcanoes erupting with immense force. These volcanoes spewed sulfur and sulfur dioxide hundreds of kilometers into space, reshaping the surface with massive lava flows and colorful sulfur deposits. Some volcanic plumes reached heights of over 190 miles, 300 kilometers, highlighting Io's extreme geological activity. This marked the first time active volcanism was observed on another celestial body beyond Earth. Scientists later understood that Io's intense volcanism is driven by tidal heating, caused by the gravitational interactions between Jupiter and its neighboring moons, Europa and Ganymede. Europa, another of Jupiter's Galilean moons, was expected to be an icy moon with a surface marked by impacts and craters, similar to other moons and planets. However, Voyager's images revealed Europa's smooth, bright surface crisscrossed with dark lines and fractures but very few craters. This indicated a much younger surface, suggesting active geological processes. The lack of craters and the network of fractures hinted at the existence of a subsurface ocean beneath Europa's icy crust. Scientists believe these fractures are caused by the rising and falling of ice, driven by tidal forces from Jupiter's gravity. This discovery raised the possibility of liquid water beneath the surface, possibly kept warm by tidal heating. These findings laid the groundwork for future missions, such as the upcoming Europa Clipper mission, which aims to explore the moon's potential habitability and search for signs of life in its hidden ocean. Before the Voyager missions, Saturn was known to have rings, but it was widely believed that Jupiter lacked a ring system. Given Jupiter's immense gravitational field, any rings would likely have been disrupted or pulled into the planet. However, Voyager discovered that Jupiter does have rings, albeit much fainter and more delicate than Saturn's. Composed mostly of dust particles generated by meteoroid impacts on Jupiter's small inner moons, these faint rings were invisible to Earth-based telescopes and detectable only with Voyager's high-resolution instruments. This discovery suggested that ring systems might be more common among giant planets than previously thought. Scientists expected Jupiter, being a massive planet, to have a strong magnetic field, but they underestimated its magnitude. Voyager's measurements revealed that Jupiter's magnetosphere is the largest structure in the solar system, extending nearly 4 million miles, 6 million kilometers, toward the Sun and forming a tail that stretches beyond Saturn's orbit. Jupiter's magnetic field is 14 times stronger than Earth's, creating intense radiation belts filled with high-energy particles. This environment poses significant challenges for spacecraft, as the radiation could damage equipment. The Voyager data transformed scientists' understanding of planetary magnetic fields and their interactions with solar winds. When Voyager 1 and Voyager 2 reached Saturn in the early 1980s, they revealed much more about its rings, atmosphere, and moons than scientists had anticipated. Prior to these missions, Saturn's rings were thought to be relatively simple, composed of broad, uniform bands of ice and rock, likely formed from a destroyed moon or comet. However, Voyager uncovered the extraordinary complexity of Saturn's rings, showing that they consist of thousands of individual ringlets and gaps. The spacecraft identified previously unknown features, such as dark radial spokes caused by interactions between tiny particles and Saturn's magnetic field, as well as the braided F-ring with twisted sections influenced by small moon-like bodies known as shepherd moons. The Cassini division, a prominent gap between the A and B rings, was found to contain many smaller ringlets rather than being entirely empty. These findings demonstrated that Saturn's rings are dynamic and shaped by gravitational interactions with its moons and possibly undiscovered moonlets. Saturn's atmosphere, previously thought to be relatively featureless, was revealed by Voyager to be dynamic and turbulent. Despite its muted colors when viewed from Earth, Saturn's atmosphere contains surprising atmospheric patterns and turbulence, challenging initial assumptions about its simplicity. Saturn's discoveries included powerful jet streams and strong winds exceeding 1,100 miles per hour, 1,770 kilometers per hour, faster than any winds on Earth or even on Jupiter. Massive storms and cyclonic systems were observed in Saturn's cloud layers, with some storm systems comparable in size to Earth. Voyager 2 captured images of a hexagonal cloud pattern at Saturn's North Pole, a mysterious geometric feature that scientists still study today. The hexagon remains a unique atmospheric phenomenon in the solar system and was completely unexpected. The complexity of Saturn's atmosphere indicated that, despite its relatively bland appearance from Earth, it is a highly active environment with unique weather systems driven by internal heat and rapid rotation. Titan, Saturn's largest moon, had long fascinated scientists due to its thick orange atmosphere. However, prior to the Voyager missions, Titan's surface remained hidden beneath this dense cloud cover. It was thought that Titan might have oceans or lakes of liquid hydrocarbons due to its dense atmosphere rich in methane. Voyager 1 performed a close flyby of Titan and discovered that its thick atmosphere was even more complex than previously thought. Titan's atmosphere was found to be rich in nitrogen, similar to Earth's, but also contained methane, hydrocarbons, and complex organic molecules. The surface remained hidden beneath thick layers of photochemical smog, so Voyager's cameras were unable to penetrate the clouds. However, the data suggested that Titan's surface could be covered in organic-rich material, potentially including lakes or seas of methane and ethane. This discovery set the stage for the Cassini-Huygens mission, which later confirmed the existence of liquid hydrocarbon lakes on Titan and studied its surface in detail. Voyager's findings hinted that Titan could have conditions similar to those of early Earth, sparking interest in its potential for prebiotic chemistry or even microbial life. Enceladus, one of Saturn's smaller moons, was initially expected to be a cold, inert body like many other small moons in the outer solar system. Scientists anticipated a heavily cratered surface with no signs of recent geological activity. Although Voyager's instruments were not able to directly confirm the presence of cryovolcanism on Enceladus, they detected hints of geological activity. The surface of Enceladus appeared unusually bright and smooth, indicating it had been resurfaced relatively recently, possibly by some internal process. Voyager data showed that certain regions of Enceladus had few impact craters, suggesting active resurfacing. These initial hints led to further investigation by the Cassini mission, which later confirmed that Enceladus is geologically active and has water ice geysers spewing from its south pole. The discovery of these geysers, combined with evidence of a subsurface ocean, has made Enceladus one of the prime targets in the search for extraterrestrial life in our solar system. It was known that Saturn, like Jupiter, had a magnetic field, but scientists expected it to be relatively weak and straightforward compared to Jupiter's. Voyager discovered that Saturn's magnetosphere is not only powerful but also highly dynamic. The magnetic field extends far beyond Saturn, creating a giant magnetosphere filled with energetic particles. Voyager found that Saturn's magnetic field is nearly perfectly aligned with its rotational axis, a surprising feature that remains a subject of scientific investigation. The interactions between Saturn's magnetosphere and its moons, especially Titan, were far more complex than anticipated. For example, Titan's atmosphere interacts with Saturn's magnetic field, creating unique plasma environments. These findings revealed that Saturn's magnetosphere is not just a scaled-down version of Jupiter's but a distinct and highly dynamic system influenced by its unique environment and moons. Next is Uranus. Voyager 2 is the only spacecraft to have visited Uranus, arriving in January 1986. It discovered 10 new moons as well as faint rings around the planet. Before Voyager 2's encounter, Uranus's moons were expected to be cold, inactive worlds. Similar to other small icy moons in the outer solar system, scientists believed they would be heavily cratered with surfaces that had not changed in billions of years. Voyager 2 revealed that some of Uranus's moons, especially the larger ones, are far more geologically complex than expected. Miranda, the innermost of Uranus's 5 largest moons, turned out to be one of the most surprising objects in the solar system. Its surface is a jumbled mix of ridges, canyons, and strange patchwork regions that suggest it experienced significant geological upheavals. Scientists were shocked to find giant cliffs, some up to 12 miles, 20 kilometers high, and features that appeared to be the result of massive resurfacing events. Miranda's bizarre landscape led to speculation that it may have been shattered by an ancient collision and reassembled, or that it experienced intense internal activity driven by tidal forces from Uranus. The other major moons, Ariel, Umbriel, Titania, and Oberon, also showed evidence of geological features like canyons, rift valleys, and signs of resurfacing. Ariel, in particular, showed the youngest surface with fewer impact craters, suggesting relatively recent geological activity. These discoveries indicated that even small icy moons far from the Sun could be geologically active, possibly due to internal heating from tidal interactions. Uranus's extreme axial tilt of 98 degrees, meaning it rotates almost on its side, was known prior to the Voyager 2 mission. Scientists expected that this tilt would have a significant impact on Uranus's seasons, but they were uncertain about how it would affect the planet's atmosphere, magnetosphere, and moons. The data from Voyager 2 showed that Uranus's axial tilt creates extreme seasonal variations, with each pole spending 42 years in continuous sunlight followed by 42 years of darkness. The tilted orientation affects the magnetic field, atmosphere, and rings, leading to unusual interactions with the solar wind and creating an asymmetric magnetosphere. The planet's moons and rings also experience extreme seasonal changes as they orbit Uranus, which may influence their surface conditions and internal activity. The combination of the planet's extreme tilt, offset magnetic field, and dynamic atmosphere painted a picture of Uranus as a truly alien world, distinct from any other planet in the solar system. Finally, Neptune. On August 25, 1989, Voyager 2 became the first and so far only spacecraft to visit Neptune, the outermost planet in our solar system. This flyby marked the end of Voyager 2's grand tour of the outer planets, providing humanity with its first close-up look at this distant, mysterious world. Given Neptune's extreme distance of about 4.3 billion kilometers, 2.7 billion miles, from the Sun, scientists had low expectations for finding significant atmospheric activity or geological features. They anticipated a cold, dark, and relatively featureless planet, much like Uranus. However, the reality of what Voyager 2 discovered at Neptune turned out to be far more surprising. Prior to Voyager 2's encounter, scientists expected Neptune to have an atmosphere somewhat similar to Uranus, cold, calm, and featureless. Given its great distance from the Sun and its faint blue appearance as seen from Earth, researchers thought Neptune would be a dormant world with minimal cloud activity and very little weather. Voyager 2 revealed that Neptune's atmosphere is actually incredibly dynamic, with some of the most intense weather systems in the solar system. The spacecraft discovered the Great Dark Spot, a massive storm system similar in scale to Jupiter's Great Red Spot. This dark, oval-shaped storm was about the size of Earth and had winds blowing at speeds of up to 1,500 m/h, 2,400 km/h, the fastest winds ever recorded in the solar system. In addition to the Great Dark Spot, Voyager 2 observed other storms like the Small Dark Spot and Scooter, a rapidly moving white cloud feature. These storms highlighted Neptune's active weather, with clouds forming and dissipating over days. Scientists were amazed to find high-altitude methane clouds casting shadows on the lower cloud layers. The presence of these clouds suggested vigorous convection currents in Neptune's atmosphere driven by internal heat rather than solar energy. Despite receiving only 1/100th of the sunlight Earth receives, Neptune's atmosphere displayed extreme turbulence and weather, which suggested that the planet has a significant internal heat source. It radiates 2.6 times more energy than it receives from the Sun, fueling its wild weather. These findings were shocking because they contradicted the expectations of a cold, placid world. Instead, Neptune proved to be one of the most meteorologically active planets, with storms that rival those of any other in the solar system. Neptune was known to have faint rings from ground-based observations, but scientists expected these rings to be sparse and relatively featureless, much like Uranus's rings. Voyager 2's observations revealed that Neptune's rings are far more complex and dynamic than anticipated. The spacecraft confirmed the existence of 5 main rings, but these rings were found to be much darker and dustier than those around Saturn or Jupiter. Voyager 2 discovered peculiar ring arcs, which are bright, clumpy segments within the outermost ring, known as the Adam's ring. These arcs, named Liberty, Equality, and Fraternity, defied expectations and added to the picture of Neptune as an active and intriguing planet. Expectations as scientists thought the arcs would spread out evenly over time due to gravitational forces. It is still a mystery how these arcs are maintained. Scientists suspect that they may be stabilized by the gravitational influence of shepherd moons, such as the moon Galatea, which orbits just inside the Atom's ring. The discovery of these arcs was surprising because it suggested that Neptune's ring system is unstable and might be relatively young, potentially forming from a disrupted moon. These rings added to the growing evidence that Neptune's system was far more complex than previously understood, with mechanisms at play that scientists are still trying to explain. Before Voyager 2, Triton, Neptune's largest moon, was thought to be a cold, inactive world similar to other distant moons in the outer solar system. Scientists expected it to have a heavily cratered surface, indicating an ancient, geologically dead landscape. Triton turned out to be one of the most fascinating and active moons discovered in the solar system. Voyager 2 revealed that Triton has a thin atmosphere composed mainly of nitrogen with trace amounts of methane. The atmosphere is extremely tenuous, with surface pressures less than 170,000 of Earth's atmosphere. The spacecraft discovered evidence of active geysers, which were spewing nitrogen gas and dust particles several kilometers into space. This was a groundbreaking discovery as it indicated that Triton is geologically active despite its extremely cold temperature of around -235 degrees Celsius -391 degrees Fahrenheit. Triton's surface was found to be relatively young and smooth, with few impact craters. It showed signs of cryovolcanism, ice volcanism, and surface renewal driven by internal heat sources. Voyager 2 also captured images of strange cantaloupe-like terrain and ice cliffs, suggesting that Triton's surface is constantly being reshaped by internal forces. These discoveries were unexpected because Triton was believed to be a frozen, lifeless world. Instead, it turned out to be an active moon with surface processes that may be driven by tidal heating due to its retrograde orbit around Neptune.